We're going to be entering the world of VSEPR today. So, if you notice, it is exciting. It's awesome. Let me get little manipulatives here we're going to actually look at later, too. So, a lot of fun stuff. Interesting, we may have a visitor tomorrow. You have to find room for her. Miss Cahill, observing. So she may be in here tomorrow, but it's interesting because last year, when she observed our class, it was the same module. Matter of fact, if she came today rather than tomorrow, it would be the same class lesson that you saw last time. And she may go, is this the only class you teach? Just this one class all year long? Right? No, trust me, we delve into the book. So what did we discuss yesterday? What was the topic of yesterday's lecture? Polyatomic ions, remember that? Polyatomic ion, it's a covalent molecule. So it's a set of atoms that have already formed a molecule because they have a bonding relationship with one another. They have shared electrons. And that shared electrons, we call that a chemical bond, and they're bonded together. They share something, so they don't want to leave it. They're stuck together as a group. And yet that group of atoms has a net charge. We mentioned before that for anything to have a neutral charge, that just meant that it had the same number of positives as negative charges. There's nothing that's without charge. Just neutral means that they're balanced. In an ion, there's an imbalance. There's either more or less electrons, the negative particles, than there are protons, the positive particles. And so typical ions we talked about before were one element, usually a metal, which wants to become positive, and a non-metal, which wants to become negative, and so they swap. You know, at that point they can swap, and that forms an ionic bond. In this case, we have positive ions, which again are going to be primarily the metals, and the vast majority of our polyatomic ions are negative, which means they're going to look for positive ions to bond with them. And so there's more than one atom bound together to form a molecule, and that entire molecule has a net charge. It has one more electron, or two more electrons, or three more electrons more than it has protons. Or in the case of ammonium, which is our exception, it has a positive one charge. It has one more proton than it has electrons. And so those ions, just like the single atom ions, the anions that we talked about before, are out there looking for an opposite charge to bond with. And so in a polyatomic molecule, you have both covalent and ionic bonds in the same molecule. You have one set that is covalently bonded together by shared electrons, and that set with its positive or negative charge is electromagnetically attracted to another ion. So there's a covalent bond within the polyatomic, and there is an ionic bond between the polyatomic and another ion. Now, when we were talking about those electron pairs, and we're kind of transitioning now into VSEPR, and you notice it's pronounced VSEPR, but it's not spelled VSEPR. It's VSEPR, right? So people just say VSEPR because they just, dyslexic. We'll just switch those two right there and make it VSEPR. But VSEPR actually stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. And I mentioned before how that when we drew the Lewis structures, that you were going to have, sometimes you would have a single electron on one side of the symbol and a single electron on the other side of the symbol. And I encouraged you to bring those two single electrons together and form pairs. The reason being is it's going to be very useful for us whenever we get into a further discussion here on VSEPR and what it means. And so VSEPR is really based upon, and geometry is based upon, your Lewis structures. The Lewis structures that you draw. So if you can't do a good Lewis structure, you're going to struggle with molecular geometries. Because here's what's happening. We are transitioning from a two-dimensional world to a three-dimensional world when we get into molecular geometry. Everything that we've shown on the whiteboard up to this point, and I've alluded to it for a few points, so I'm not going to say absolutely everything, because I think I did draw a three-dimensional Lewis structure on the board one time. But whenever we draw our Lewis structures, we are generally thinking of something that exists in two dimensions, or at least in our mind exists in two dimensions. Let me go ahead and see if I can get this thing to advance. I can't because we have a frozen screen. Let me get back. Let's unfreeze this. Yes, sir. Would you like to get it? You may. Mm-hmm. Give Aaron just an opportunity here. Get his book. So, if I were to draw this methane molecule, Lewis structure for it, the CH4, in this case, I've left, there are no electrons that I've left off. There are occasionally times that you're going to see in these PowerPoint slides, and I'll try to remember to refer to these, but I will leave some of the extra valence electrons off. Like if this was a CCl4 molecule, I may very well not have the 6 double electron sets. The 3 pairs form the 6 electrons, and then the bonded. But I'll try to call that, because sometimes it just gets too cluttered. I want to remind you, though, that they technically are still there. In this case, however, hydrogen doesn't want to have an octet. It wants to have just 2. And so what we see here is a full Lewis structure for methane, CH4. Now, the thing about this diagram here is it's a 2-dimensional diagram. I mean, if you looked at this diagram and you said, okay, what we're talking about now is transitioning from 2-dimensional to 3-dimensional. It's kind of the way of looking at a square versus looking at a cube. See? It took me a little bit more time to draw the cube than it would take me to draw a square. Because when I draw something in 3 dimensions, we get this idea of vanishing point and all that kind of thing. We're trying to visualize something that has a 3 dimensions to it. And the world we know is actually 3-dimensional, or 4-dimensional, however you want to look at that, if you include time as a 4th dimension. So we kind of relate to 3rd dimensions and 4th dimensions. For example, as I'm looking out you all here, you are looking towards me, you understand that there's some depth, that I'm not a flat man here, right? If I turn sideways, you can still see me, because I have depth. And when you're in a room, there's one axis going in this direction, there's another axis going in this direction, there's a 3rd axis going in this direction, and then we move through it in time in those 3 dimensions. If I draw a picture on the board like this and say, this is what a methane molecule looks like, it's kind of presenting it as if it's flat. If I looked at the side here, and truly were 2 dimensions, if I looked in from the side, I wouldn't see anything, because it doesn't have any depth to it. And we know that's not the case. If I draw on the board the difference between a circle, and I tell you that this is actually a sphere, what does that do in your mind? It takes it from being an empty circle like a ring and turns it into a beach ball. You see? And how you visualize it matters when we get into geometries, because this is what we're doing. We're going from something that shows it in 2 dimensions, which is a way to represent it as long as you realize that's not the way it really looks, and then moving it in 3 dimensions. If I live in a house, I could give you the idea of house by drawing something like this. And you get the idea, okay, that represents a house. No windows, boring place to live, but that represents a house. Is that what a house, the idea of house here is just a 2-dimensional flat picture. If I instead were to draw the same kind of a front to it, but say that, it's not flat like that, it's actually in 3 dimensions, and you'd have a better sense of how much that house took up in actual space. Like if they're all flat, we could put an infinite number of houses on a lot, because there's no depth to them. You just pile them all up. Actually, you wouldn't be piling them up. You're just laying them over top of each other. But 3-dimensionally, wait a minute, you need to have space. You need to have room between them. And that's the kind of idea we're going to transition now to 2-dimensional to 3-dimensional Lewis structures. Now, you have seen some Lewis structures represented in 3 dimensions and haven't realized it yet. I think we get a couple examples. You go, yeah, I noticed that in the book. I saw it drawn this way rather than that way. Why did they do it this way? Why did they do it in a way that I didn't quite expect? Well, in a couple cases, the book has gone ahead and shown a Lewis structure in a 3-dimensional kind of a view, but it was so close to the 2-dimensional kind of view, it didn't really stand out to you as being that much different. But there are plenty of other molecules where it is quite different. Now, moving into 3 dimensions, we have to realize, first of all, like if we look at this in just 2 dimensions, let's pretend it's 2-dimensional. I've got a carbon and hydrogens, that there are forces at play in this molecule that are defining the geometries. And these forces at play set not only this geometry, but every other methane molecule experiences the same exact forces and results in the same exact shape. So every shape that we're going to talk about is a result of the forces opposing one another, forces exerting pressure, and the resultant move, if you will, of those forces. So for this discussion on three-dimension Lewis structures, which is VSEPR, the molecular geometry, I want you to think of this as, I sometimes in the past have referred to this central atom as a pivot point. It's a hinge. It's that place that these other atoms that are bonded to it pivot about. They move about. Let's pretend, for example, that rather than the carbon being just a symbol in the middle, that it's actually like a pin or a hinge, and each one of these each one of these bonds represents a leg, and at the end of each of these is a hydrogen. Okay? That there are forces between the carbons and the hydrogens, and that force between the carbons and the hydrogens is this bond that's holding them together. So the hydrogens aren't going to just simply fly away. They're bound to the carbon, but how are they going to relate to one another? Well, there are forces at play where this hydrogen and this hydrogen are pushing away from each other. Okay? So if we only had two hydrogens in this molecule, all we had was a carbon and these two hydrogens, and those two hydrogens wanted to be as far apart as possible and yet still be connected to the carbon, what would they do? Well, if these two weren't present, it was just the carbon and these two hydrogens, and these two were repelling one another, wouldn't this hydrogen swing all the way down to the bottom? They want to get as far apart as possible and yet not lose their connection to the carbon. See that? So whereas now they're at 12 o'clock and 3 o'clock position, if they were the only two, this would swing down to the 6 o'clock position. If it went past 6 o'clock, what would it be doing? It would actually be getting closer again from the other side. So it would be pushed back again. So we're going to see that this hydrogen, if there were only two of them, if it was a CH2 molecule, that this hydrogen would actually be exactly 180 degrees away from the other. If it's past 180 degrees, it's getting closer, it can be pushed away. If it gets farther this way, to this side, it gets pushed back away. And it forms what we're going to come to find is a linear molecule. It's going to be a straight line. So just speculate right now, rather than a CH4 molecule, let's pretend it was a CH3 molecule with just these kind of bonds. It's pretend, you know. Let's just make this up. We have a carbon, we've got three hydrogens. What would happen? They would push each other apart so that they would be equally separate from one another, wouldn't they? And if we had three of them, what would the angle be between all of them? In the first example I used, we had a central carbon. And let's get rid of the carbon and hydrogen. Let's just use this idea of, okay, here's a center point. And I have bound to that center point, let's just give it something a positive charge there. It's an awful marker. So let's pretend we've got a central point here, and we'll give it a common charge of a positive, and it's stuck to that positive by an arm. And I put another positive leg on this thing, and these two are repelling one another. The forces that are repelling it would cause this leg to go exactly opposite the other, because if it moves this way, it's getting closer. If it moves this way, it's getting closer. It is stuck in a place that is as far away as it can get and still stay connected to the pivot point. All right? And we said that the angle between those two, since it's a straight line, what is the angle here? I don't know if we did say it. Whereas this shows a 90-degree angle, this right here would be 180 degrees, right? Okay. Now let's change it up again. Let's go ahead and add another arm. Let's pretend that we were able to just add another arm onto here, and this one is now positive. So we have three positives around this hinge point or this pivot point. All three of these are going to try to do exactly the same thing. They're going to try to get as far away from one another as they can get. So what would the resulting shape look like? They're trying to get as far from each other as they can and still not lose their connection to the pivot point. And as they push away from each other, they're going to find this place of equilibrium where if they move in any direction, they're actually getting closer. They're forced to be the same distance apart. In this case, what is the angle? It's 120 degrees. In the first case, when we had a straight line, it was 360 divided by 2, which equals 180. Okay? In this case, we have 3 connection points, which is 360 degrees divided by 3, which is equal to 120 degrees. So in this example here, if we have 3 different legs that are all repelling one another equally, all not willing to give up their connection to the pivot point, but wanting to get as far away from each other as possible, they would move to 120 degrees apart. And in the final case, in this case here where we have 4 of them, they're pushing to be as far apart from each other as possible, and so they actually result in an angle of 90 degrees. So in 2 dimensions, this has all been 2-dimensional, right? When we talk in 2 dimensions, we can have 2 legs which want to be 180 degrees apart, 3 legs which wants to be 120 degrees apart, and 4 legs that want to be 90 degrees apart. Which is why up to this point you may have seen a molecule which had a central atom and had 3 other atoms connected to it. And you may have seen it in your book, and it may have looked something like this, like a central point here and here. Or you may have seen it in your book written like this, and not really picked up on the fact that, hey, they're showing me something that this is an acceptable way to draw the Lewis diagram, but this is actually what it's going to look like in 3 dimensions. It's actually going to be pushed away so that they're evenly distributed. But here's the rub. This is all actually review kind of from what we've done before in terms of the Lewis diagrams. And I think in 2 dimensions, this makes sense. At least I hope it does. Should be pretty straightforward. If I have 2 of them, they're going to be 180 degrees apart. If I have 3 of them, they're going to be 120 degrees apart. If I have 4 of them, they're going to be 90 degrees apart. The difficulty is, or the additional difficulty is, that we're not talking about life in 2 dimensions. We're going to talk about life in 3 dimensions. And just as my little picture of a house in 2 dimensions is pretty straightforward to draw, just, 3 sides of a square and a roof on it. When I go to 3 dimensions, I've got to take into the depth and the perspective and all that kind of thing. We have to do that when we consider the geometries of a molecule in real life in 3 dimensions. And what that means is it's not going to represent itself perfectly visually to us as a 90-degree angle. Like I said before, over here, let's say I'm starting to draw up this same molecule, and I'm going to draw this methane molecule, the CH4 molecule. This is what it looks like in a 2-dimensional Lewis structure. What is it going to look like in a 3-dimensional Lewis structure? So even though I'm not showing you here what it would look like if it only had 2 hydrogens. What I'm showing you here is we're starting to build this molecule up from this. We're going to represent the same thing. So I'm just showing you part of the drawing right here. And we're going to add to it as we go through. All right. Now, the key thing you need to remember is that when we move from 2-dimensional to 3-dimensional geometries, I said that if we have 4 connecting points, if we had 4 legs, and they're equally distant apart, that they would be 90 degrees apart. And again, I hope that makes sense to you. They'd be at all the cardinal positions. And it's not because it's Louisville, okay? It's not the same thing. Cardinal positions, 12, 3, 6, and 9 o'clock. When we take a 2-dimensional picture and we move to a 3-dimensional picture, and we make those things be as far apart as possible, the angle is no longer 90 degrees. It's actually going to come back to be, let me draw it up for you, 109 degrees. 109 degrees. So having something to be equally distant from one another angularly in 3 dimensions, if I have 4 connecting points to this central hinge element there, the central hinge element here at carbon, 4 connecting points, we show it in 2 dimensions as 90 degrees. Because we're not taking into account that some of this molecule actually can come forward out of the board, and some of it can actually be back behind the board because this isn't a flat molecule. It actually exists in 3 dimensions. 90 degrees in 2 dimensions is equal to 109 degrees in 3 dimensions. So if you have to work this thing in your mind of saying, wait a minute, it's 4, that would be 90, but in 3 dimensions, 90 and 2 equals 109 and 3, that'll work for you, okay? And actually, we're going to start with the most number of connections and learn each geometry going backwards, starting from everything being equal. A central element here being carbon, and 4 connection points, all being hydrogen. They all are identical to one another. They're all moving to be equally distant from each other. They're all repelling one another, and yet keeping their connection to the central carbon. And when they do that, they orient themselves around that central element by a bond angle. It's called the bond angle, a bond angle of 109 degrees. Let's see, how many? I have several of these. Let's see, 1, 2, 3, 4. I have 11 or so with me here. Let's just start passing them out, like say every couple. Why don't you guys share across the aisle? Let me pass back this row and share with a partner on this side. Same thing, you guys here, and share on this side. Aaron's going to have your own. Here you go. Each of you take one of those. Okay. Yeah, go ahead and pass them back. I've got a couple extra. No. It's not that hard, guys. I passed it. I expect you to pass it back in the row. Each one of you, like in this row, get one, and then you have a partner beside you that you can show it to. Like over here, pass it down the row. You have somebody here you can share it with. Okay? Anybody like? I've got maybe one more. Who wants their own? Here I am throwing molecules around. All right. I want you to look at this in your hand. It's manipulative right here. What you have in your hand is a way to represent this shape. A central atom, the pivot point. And most of these, I believe that's black. I tried to use black because carbon and black, they're always shown that way. But you've got a carbon in the middle, a central pivot atom, and then you have 4 different legs. And it may not look at it as you just, stare at this, but the distance between every leg here on this is 109 degrees. In any way you look at it, it's 109 degrees, the angle between them. This is what it looks like when those 4 connected points move as far apart from one another as they can get. If any one of these legs were to be shifted in any direction, it would no longer be as far away from every other point as it can possibly be. And the forces would cause it to go back to a position of 109 degrees because that is as far as it can be without getting closer to something else. All right? Because if I really wanted to mess this up, in the manipulative you have in your hand, the central atom, the pivot atom is in the center. These are the exterior atoms, and every one of these little straws represent one of these bonds. They represent these 2 sharing an electron. This is the electron pair. And just the name VSEPR, valence shell electron pair repulsion, these pairs are all pushing away from one another, forcing these atoms to be the same distance apart from one another into the shape of 109 degrees. All right? Now, the name of this shape right here, you're going to need to just have these memorized. 109 degrees is the tetrahedral. This is a tetrahedral. Tetra, remember, means 4. It's a 4-sided figure, a tetrahedron here. Okay. So the tetrahedral has a 109-degree bond angle. And it looks, this is the way we would draw it in 2 dimensions. This is a 3-dimensional drawing in a 2-dimensional space. So let me show you over there in just a minute what those different symbols mean. I want you to take your manipulative in your hand like that. I want you to hold it so that you're looking at the central pivot and that you're also seeing these 2 legs and lay them down as if it was flat on the board like that. See? If I take my hand and I hold it like this, I hold one straight up and I hold it in my hand like this and let your hand represent the board. Or whatever you're drawing, like if you're drawing it on a piece of paper, your hand represents the paper. If I do this so that I can see where the paper would be, and I say, okay, this leg, the vertical leg there is this leg, And this angle over here to the right at about 4 o'clock, it's this leg. The angle there is 109 degrees. But the angle here is 109 degrees. 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 They're all 109 degrees. But how do I show 3 dimensions in 2 dimensions? Well, as I hold it like this, you're going to notice that one of the legs in the back, it's sticking back in space, right? It's sticking behind where the plane of the board or the plane of the paper, or in this case, the plane of your hand is located. One is sticking backwards, away from you. And we represent that leg that's pushing away from you or behind you. It actually would be into the board. We represent that with this dotted line. A dotted line means that in 3 dimensions, that leg and the associated atom is actually behind the board. And so you get the idea that it's pushed back behind. And after a while of seeing this, you'll just look at this molecule and you won't think, hey, why is it flat with a dotted line? You'll say, oh, that means that bond right there is actually in space behind the board. So again, showing a 3-dimensional object in 2 dimensions, we do it by this one in the back having this dotted line. And the one that's forward, if I again hold the plane vertical, I've got one back and one coming forward, one coming towards me. And we try to represent that one in 3 dimensions. By this symbology here, it's kind of this long triangle. And this represents this leg coming forward out of the board. It's coming out towards you. So this leg is actually going, in 3 dimensions, would go back into the board. This leg would come out of the board. And these two would be in the plane of the board. Do you see it? Okay. So we're trying to represent this shape. And because it's not a flat world, it's a 3-dimensional world, this is a 3-dimensional representation of that, and we draw it using those symbologies to show the bond in the back and the bond coming forward. And that's a tetrahedral. Now, each one of these shapes is significant, but the way I teach it and the way I learned it, the next couple shapes are all based upon this. So you need to understand this one before we move on to the next one. Okay? Now, this is a pyramidal. A pyramidal is, think of it just as you have the tetrahedral in your hand. And let's go ahead and take off one of the bonds. Take off one of the elements. Remove it, right? Yep, do it. Go ahead and just, these are like Legos or Rector sets. They just stick together, they pull apart. So just pull one off. Now, how does this differ from what we just looked at? The last time we had 4 connecting atoms around a central pivot atom, right? We had 4 of them. Now we only have 3. Whereas before we had a hydrogen bonded up here, now we only have 3 hydrogen atoms, and instead of a 4th bonded hydrogen, we have an unbonded pair. Now here's one of the other principles you're going to need to remember all the time, is that if each one of these pairs was repelling one another, VSEPR shell electron pair repulsion, okay? If every one of these were repelling each other at the same strength, it would be 109 degrees, right? Because let's see, we've got a pair here that's being shared, a pair here that's being shared, a pair here that's being shared, a pair here that's not being shared, right? Nitrogen hasn't given up any of those two. Those two still belong fully to nitrogen. They're not sharing with anybody. But the other ones are shared. And so remember this concept. If all 4 of those different points had the same strength, they would all repel one another to go to 109 degrees. But that's not the case. An unbonded pair exerts more force than a bonded pair. I didn't say take them all apart. Yeah. Okay? So an unbonded pair exerts more force on the other angles, or on the other pairs, than the bonded pairs do. You might want to think of it this way. This pair is staying put next to the nitrogen. These other ones are being shared back and forth, and they're not present in this domain to push in the same way. These ones are just exerting force all the time. However you remember it. This pair exerts more force than it would exert if it was a bonded pair. And because it exerts more force, what would you suspect that would do to the geometry? Picture retakes, I think that is. Give it to somebody else. Anybody else want one? Somebody take the tetrahedral. I don't know. If you get done early, you can come back. If not, they'll be here. That's fine. All right, so consider for a moment what this shape is going to look like compared to the tetrahedral. If I told you before that if it had 4 hydrogens, if this were a bonded pair, that this would be 109 degrees. And this would be 109 degrees. And this would be 109 degrees. Okay? But if I tell you that because this is not a bonded pair, it's an unbonded pair, what does that tell you it's going to do? If it's an unbonded pair, if it exerts more force than a bonded pair does, what do you think that's going to do to resulting angles? If a bonded pair pushed away and caused 109 degrees, what would an unbonded pair do if it pushes harder than a bonded pair? It would push all the other legs down, wouldn't it? Wouldn't it make this angle greater? Well, actually, I'm just going to write it as 109 plus, because you don't need to know what that angle is. That's not that significant. It would push harder, right? It's going to push them down away farther. And the remaining 3, because they're all being pushed down by this pair harder, what are they going to do? Are they going to go farther apart or closer together? Closer together. So the resulting angle here is going to be less than, between these bonds, is going to be less than 109 degrees. Why? Because the push away from this unbonded pair is greater than 109 degrees. So all of the legs need to be pushed in a little bit tighter, and the resulting angle is 107 degrees. It's 107 degrees between all of these different legs. Okay? The bond angle between them is all 107 degrees. A little bit less than 109. Why? Because this unbonded pair pushes a little bit harder than the force needed to make it 109. Please. And the resulting image here, the pyramidal, actually the way I teach it is, look at this for a second and consider the camera right over here that's taking my picture, okay? See the tripod? Look at the 3 legs down below, right? The 3 legs down below. Now that has a long neck on it right now holding the camera higher. But if you looked at the base, you see 3 legs coming out from the center portion here, and then the camera on the top. And so what I tell people to remember is, think of this as a tripod holding a camera. It's a tripod holding the camera, and it's set up where the camera is, the angle here is greater than the angle here. So this is a greater angle, and this is a lesser angle. And just like that tripod, the distance between all of those bottom legs is the same. And they're pushed away from the camera that sits on top. And so that right there is called a pyramidal. It looks like a pyramid, doesn't it? I mean, in 3 dimensions, you've got the different sides of the base there. Again, this is a 3-dimensional pyramid. It looks like that. It's a pyramidal and not a tetrahedral. So the pyramidal starts off, we think about a tetrahedral, and then we remove one of the pair. Now, if you look at the manipulative in your hand, this unbonded pair represented here by this little nub on the top. The little nub represents an electron pair, an unbonded electron pair, and it's going to be pushing down. So this is not technically correct anymore. The angle should have changed. It would be slightly down, but you know what? They're not going to build a whole new manipulative for 2 degrees. You just need to remember, when there's 4 connections, it's a tetrahedral, it's 109. When there's 3 connections, it's a pyramidal, and the pyramidal angle is 107. It's 107 degrees between the bonded pairs. the bond angle. Water molecule. In 2 dimensions, you may have seen it drawn like this. In 3 dimensions, we don't get into, this is a bent molecule. So we've had tetrahedral, pyramidal, and now bent. And a bent molecule, we can draw a bent molecule without using any 3-dimensional symbologies. Remember the last one? Even here, it has many of the same symbologies as the tetrahedral did. This leg is back into the board. This leg is coming forward out of the board. This electron pair and this bond are on the plane of the board. When we go to the bent molecule, we're not going to represent it with any bond angles that are behind or in front of the board. We can actually draw the angles of the bonds in the plane of the board and represent the unbonded electron pairs like this. Now, if before one unbonded pair exerted more force than a bonded pair, and we had one of them in the pyramidal, here we have 2 unbonded pairs. And the 2 unbonded pairs here, each one of them exerts more force than any one of the bonded pairs. So just thinking through that logically, what does that mean is going to happen in this shape? If it was equal, it would be 109, right? But it's not equal. And if it was one unbonded pair, it would squeeze it in. If it had 3 legs and one unbonded pair, it'd be 107 degrees. In this case, we've got 2 unbonded pairs, and those 2 unbonded pairs are both pushing harder than those 2 bonded pairs, meaning it's going to squeeze together even more, resulting in a bond angle of 105 degrees. So again, we're going to learn it as 109, 107, 105. Those are the 3 different angles. It's 109 degrees in a tetrahedral, 107 degrees in a pyramidal, and 105 degrees in a bent molecule. It's a bent molecule because it has 2 bonded elements to a central element, and it has 2 unbonded pairs. And the net result is a bond angle, the angle between the bonded pairs, of 105 degrees. Third case is a triagonal. Now, there are charts and things like this in your book. If you get confused, you'd be able to review them. But a triagonal. Now, we're no longer using this. This doesn't apply anymore, our little tetrahedral. So make sure that you have these available in the class for me to pick them up. We're going to take a look at this one. This is a triagonal. Now, the interesting thing about a triagonal is it also exists in a way that we can represent it in the plane of the board. We're not going to have any angles that are in front of or behind. So there's no dotted lines and there's no long triangles that are being used to represent an angle that's behind the board and an angle that's in front of coming out of the board. It's all going to be represented in the plane of the board. But there is something that happens to the angles. Now, in this case here, you've got 2 hydrogens, each bonded with a pair, and here you've got a double bonded oxygen. And for molecular geometries, the fact that it's a single bond or it's a double bond is not going to come into play. A single bond and a double bond, both just are going to represent a bond. Okay? So we don't need to, the fact that it's a double as opposed to a single is not going to affect the way we understand the geometry in 3 dimensions. But as I mentioned on the board before, now we have a central pivot atom with 3 bonded. These 3 are exerting force, and it's not really the 3 elements, it's the bonding pair is exerting a certain force to create a shape. And since we have 3 around a central and they're all trying to get as far apart from one another as possible, what would the resulting angles be? 3 things trying to be as far apart as possible in a circle. So 360 divided by 1, 2, 3 pieces. If you had a piece of pie, if you had a pie and 3 people are going to share it, you cut it in 3 pieces, each piece being the same, each piece would be 120 degrees. So every angle in here in the bond angle is going to be 120 degrees. But it's going to be 120 degrees, and they're all going to be represented in a flat plane. None of these angles is coming forward or going back. Because if any one of them came forward, it would be getting closer to the other side. It would cause the whole thing to rotate. So the opposing forces create this equilibrium point, this balance point, and the balance point is going to be 120 degrees, all represented in the plane of the board. None of them coming forward, none of them going back. The last one we're going to talk about is a linear molecule. The linear molecule. We mentioned that when we have an angle with a central pivot atom and two other atoms, but there's another case. For example, they use in the book, they talk about the homonuclear diatomics. The homonuclear diatomics, you remember, are two elements that exist naturally in the molecular form rather than the atomic form, in the sense of O2, H2, N2, Cl2, F2. The homonuclear diatomics, they form bonds between like atoms, and they exist as a molecule of two of them bonded together. I said we're not going to normally find nitrogen as a single nitrogen atom. We're going to tend to find nitrogen bonded with another nitrogen to form an N2 molecule. And what happens when, in this case, we're using chlorine as an example, when chlorine and chlorine, when two chlorines come together and they form this covalent bond between them to form a Cl2 molecule, this is considered to be a linear molecule. This is actually a molecule that doesn't have a pivot point. It's just two individual atoms bonded together. And so if it lacks a pivot point, if it's just two molecules, it's going to be considered a linear angle. The angle here between these two is 180 degrees. It's a straight line. Okay. So this is kind of an exception to what we've been talking about to this point. In three-dimensional geometries, every single geometry has had a central pivot atom. In this case, there is no pivot atom. It's only two atoms to form a molecule, and because that's the case, it's considered to be a linear. The bond angle here is 180 degrees because there's only two of them. You can rotate this thing any direction you want, but the bond angle between the two is always going to be linear, 180 degrees. Because this chlorine's not going to get any closer or any farther, there's always going to be bonded in that orientation. But we do have examples where there are atoms that are bonded together. Three of them, for example. Here, CO2, carbon dioxide. We're representing here a carbon and two oxygens. By doing the correct Lewis structure, we find out that there are a double bond between the carbons and the oxygens, and that there are two unbonded pairs on each of the oxygens. And since we do have a pivot molecule, or excuse me, a pivot atom, carbon is our pivot, there is a possibility that if there's a shape, it's going to be shaped around our pivot atom in the middle. In this case, there are only two connection points. Those two want to be as far apart as possible, and the way they're able to attain that is to move around so that they're exactly 180 degrees apart. They form a linear angle of 180 degrees. Now, to take this one step further, I want to show you how you may have seen the CO2 molecule represented. And this is a two-dimensional Lewis structure, and this is the three-dimensional Lewis structure. See, there's very little difference between the two. It's still shown in the plane of the board. You can still do the same thing. There's no bond that's coming out. There's no bond that's going back. They're all being represented in the plane of the board. But the only thing that's different is, notice the unbonded pairs. In a two-dimensional Lewis structure, we just show the two pairs, in this case at the 9 o'clock position and the 6 o'clock position. And for symmetry, I did the same thing over here, 6 o'clock position and the 3 o'clock position. But when we go to the three-dimensional Lewis structure, to look at the molecular geometries, we take these electron pairs and we put them at the diagonal, because as you look at it, I've got one set, two sets, three sets. I'm going to represent them in a way that shows that they're going to try to be as far apart from each other as possible. And we do that by setting these angles and depicting them on the slants like that. So same thing on the other side. So you may have seen a molecule written like this, And maybe as you're doing two-dimensional Lewis structures in the past, it didn't quite strike you that, hey, that's a little bit different than the way I learned it before. I wouldn't expect it to be kitty corner like that or on the diagonal. But what they're trying to represent here is that these electron pairs are trying to move away from each other and move away from this bond as well. And so they depict them on the angle. So table 5.2 in third edition, I'm assuming it's going to be table 9.2 in second edition, but it gives you a summary of all of these different molecules, their structures, their bonded pairs, their unbonded pairs, and the resulting shapes. You can see every one of them again. So the only question then is, once you look at this table and basically memorize table 5.2 in the sense of once you draw a good Lewis structure by looking at it, you should be able to then determine how to draw the three-dimensional VSEPR diagram, and from that diagram be able to draw the molecular, to be able to determine the bond angles, to put them back in place.